to record. Please, Stéphane, you can start.
Oh, it will be very short because I explained to Rosa, I have completely forgotten that I have to give some news. So what we are doing now is that we are doing the test of the telescope at 2HP. For example, tonight, the colleagues are had 2HP to make the test of the telescope. So now we're testing the telescope without any instrument. We just have a simple camera at the Nasmith focal plane. And then we expect to receive, we have to check with Alan, the Dragito, which is the small version of Drago, which is a visible instrument. And we expect to receive, I think, Dragito in 1 month. There is some administrative problem. Dragito is ready, intact. So now we are solving all the details, I would say double quote, this kind of details. You can spend a huge amount of time to solve all this administrative problem. But okay, everything is in the pipeline. So we expect to receive Dragito in 1 month, 2 months at max. So after we make the test of the telescope with Dragito. And here with Dragito, just to be clear, the telescope alone, the image quality is perfect in the center, but very quickly the image quality is very bad when you go, you are leaving the center of the field. So with Dragito, it will be possible to test completely the image quality because there is the field corrector, there is 3 lens, the field corrector with Dragito, so it will be possible to characterize completely the image quality of the telescope. So that's all. I hope to be able to send you, I think, when we receive Dragito, a nice image delivered by the COLIBRI.
Okay. If there some question, any question, or I don't know, maybe William or Ro or Fer want to add something, Jorge?
No, I don't think I have anything to add to what Stéphane said. We're in the process of doing the export for Dragito, and the environmental permit documentation has been submitted to Semarnat last week. I think that's all.
But something which is very clear that we have no visibility in our capacity to go to Mexico.
Yes.
So it's bon, this year it will be an extra very strange year. So we will see.
Another one.
Yeah, the last one, I think.
I hope so.
No.
Yes.
So for the LIA, maybe we'll have to take a decision at the next meeting in June if we try to organize a physical meeting. Not sure this year.
I agree.
Sure. Because I don't know the situation in Mexico exactly, but in France, the fact you can.
Vaccination is proceeding slowly.
I think in France, Macron has announced that in July or August, almost everybody will be vaccinated. But bon, we will see.
But we don't believe it.
I confirm.
Right. Same here. Okay. That's all I have, Rosa.
Okay, if we don't have more news, we can start with the talks. Susanna, please, could you share your screen?
Yes, so let's see if we can share the screen, if everything is working. Just a second. Here is the screen, but I have to go there. So just a second. Here and then this. Okay, just a second. I stop sharing for a moment and then I start sharing again because I had a problem. Okay. Share. Yeah, but I don't see anything here.
You have a 2 screen?
We can see your screen.
Yes.
Do you see the screen?
Yep.
No. Yeah, but you don't see the presentation, right?
Yeah,
No.
we do.
No, Yes, click on play. If you click on play, it doesn't.
You see it?
Yes,
Yes.
perfect.
Ah,
Perfectly.
no, no.
No.
But we
Ah.
also see
Oh.
the presenter notes.
Instead I saw the, okay, for me it's the opposite, so I'm sorry. Let's see what we can do. So, let's try again. Share screen, share. Yeah, but I think it will do the same. I don't know what's happening anyway.
I think you have to share your whole screen, not only one.
Yeah, I shared your screen, but I don't know why, because now if I play, it will happen as before, right? Let me check. Yes, it says before, right?
Yes.
So, okay, I will simply do another thing. Sorry about that. Okay, so. Okay, in principle, now you see the presentation. Is it correct?
Yes.
Perfectly.
Did you see my mouse?
Yep.
Okay, and okay, you see that I changed the slide? Yes.
Yes.
Okay, perfect. So sorry about that. So Stéphane asked me to talk about the Stargate collaboration. And in fact, since this collaboration, or at least the core of the collaboration, it exists since years. To really talk about the collaboration, we are kind of the same people doing the same job since the 10 years, even more, 20 years now, more or less. So it's more a talk on the past, present, and future of the GRB follow-up at ESO VLT that nowadays is done by collaboration that is called Stargate, but okay, names can evolve and change, but the core people and the science is the same. So I start with some word about the beginning of these studies of afterglow follow-up at ESO VLT, Very Large Telescope. So first of all, I wanted to show you here, especially if there are students, some historical data. That is the data on the first X-ray afterglow ever detected of a gamma ray burst, and also the first optical counterpart. Sorry? Okay, was not.
Go ahead.
Okay, so, and the first optical counterpart, fine. So this was an exceptional step forward in GRB astrophysics, thanks mainly to the BEPOSAT satellite that brought this X-ray detection. Then another huge step forward came with the first optical spectrum detected. That is not the one associated with this event, but is an event a few months later. Why? Because it was the definitive, let's say it confirmed definitively that we were dealing with a cosmological event. So the origin was extragalactic. And also, after having taken the spectra, we immediately the community immediately saw the perspective that could open thanks to GRB afterglow spectroscopy, because in fact we had powerful beacons that could allow us, sorry, it's not possible to go. Okay, that could allow us to study the galaxies where the GRB exploded, and also the IGM up to pretty high redshift, let's say. Why? Because we have this very luminous afterglow light, okay, that if we observe the spectra that reached our telescope, we have in the spectra all the absorption lines from the gas that absorb this light of those galaxies, but also of the IGM and all the intervening system, okay? So people start saying, fine, if we have gamma ray bursts exploding and high redshift and the afterglow are bright enough, this really opened the opportunity to study galaxies in details up to the very high redshift. So what do we have in the spectra really as features? We can have, this is a very nice case, we can have metals absorption lines here, so we can study the metal content of the gas that the afterglow light crossed. And also we can have the neutral hydrogen absorption lines, in particular the neutral hydrogen of the Austin galaxy. So we can also monitor the neutral hydrogen content of galaxies and measure metallicities, taking metals and neutral hydrogen into account very precisely. We can measure metallicities. Then we can also study the IgM through the absorption line forest here on the blue side of the Lyman alpha absorption. And we can also investigate some possible photons escaping below the Lyman limit. Okay, so the spectra are really rich of information. And this detection of the afterglow of gamma ray burst really made possible to enlarge the interest of gamma ray burst, because of course gamma ray burst, we can observe the afterglow to study the physics of these extreme phenomena, okay, so in terms of the physics of the jet, for example, but we can also use them to study galaxies, and why not try to have some information on ionization, and also they are also tools to study stellar evolution, because they are linked to the evolution of massive stars or neutron star binary systems. So VLT was very soon a main let's say, plays very soon a major part in this kind of studies, because the first light of VLT is in 1998, so just 1 year after the afterglow discovery, and it was open to the community in 1999. It was already equipped with what is called the target of opportunity mode. That is very important. That is that even with this huge telescope, we could have observing programs that were able to say, okay, you interrupt the schedule that you have, and in some hours or tomorrow, you will go and look at the target of interest. So these are targets that are not, let's say, steady targets, are transients. And so one cannot predict when they turn on. And to observe them, ESO use this target of opportunity mode that is still in place, actually. So this I found very, very interesting to look at some of the first observations that were performed with VLT. So here I show you some observation performed with FORCE instrument that is able to do photometry and spectroscopy. Okay, so at the beginning we had very large error regions, or from the gamma ray satellites, or in the best cases when we had an X-ray counterpart, as I said, from Bepo-Sachs, but Bepo-Sachs was dismissed pretty soon. And so we had also to search for the optical counterpart, okay? In that epoch, there were almost no robotic telescope, we say none. So even with VLT, we had really to look for the optical counterpart, and then to follow up with the photometric and spectroscopic observations. I show you here, for example, some photometry that were used to build spectral energy distributions, so as to fit them with models that were, let's say, able to try to constrain the dust property, because thanks to gamma ray burst afterglow, we can perform also some dust studies for very redshift galaxies. This is a spectra that was taken a week after the burst explosions. Makes me laughing, because now we do the spectroscopy is or the same night or the day after, or we drop it. So here the signal to noise, of course, is very poor, because the source was already pretty faint, but it was possible to determine the redshift and to this break, that is the Lyman break. That means this is the Lyman alpha, the neutral hydrogen of the host galaxies, and in the IgM that absorb the optical flux. So you have a huge break, and it was possible to determine a redshift of 4.5. Here is the light curve in points of this gamma ray burst afterglow. So as you can see, the observation started 84 hours after the burst. And anyway, they were kind of bright enough to be followed by force. And we had also kind of a lot of time available, because those were new phenomena with a lot of unknown, a lot of potential. So we had kind of significant time available at the telescopes to follow up these events. Okay, here are other light curves of other bursts that exploded before that one and were followed by or VLT or other instrument. I just chose to show you this plot because you can see that there were even observations starting. This is in days, so this is 1 day. Okay, so we had observations starting days after the burst, even up to more than a week. And very rarely we had observation after, let's say, 10 hours or so. And it was really, really very rare to be able to observe within the first hours. This is another example of a burst 2 months after the one that I showed you before. So here again, I wanted to show you some photometric observation to follow up the light curve, and that allowed to show the presence of a break, so a jet break here. Of course, with this observation, one of the goals was to use this observation to test all the afterglow models that were produced in the literature, and those were the first samples to test them. So of course, this is the prediction of the spectral and temporal behavior of GRB afterglows. And so all the parameters and also this behavior had to be confirmed by these first samples of observation of afterglow light curves. So here, as I said, we have a jet break, and this is a spectrum of the same GRB, even 5 days after, between 4 and 5 days after the burst explosion. Okay, so with the decent signal to noise and very small lines. So this could also be considered as a short gamma ray burst. So you can see it as an example of one of the few spectra of short gamma ray burst. So of course, since we didn't have any rapid information of the location of the precise information on the location of the gamma ray burst, we had to wait days, as I show you, to perform the observations, to wait to have the information from the satellites, and also to be able to detect the counterpart within large error regions coming from the satellites. So our sample was greatly biased against the faintest sources, okay, because we were only observing sources that were still bright after days, as these ones, for example, that is a magnitude 20 something after even a day, more than 1 day, more than, yes, sorry, 1 day after the explosion, so 20 point something. So then another amazing, let's say, results that has been obtained also thanks to the VLT instrument is the association of supernovae with gamma ray bursts, of core collapse supernovae with gamma ray bursts. We had already the example of 98BW that was detected without VLT. But in that case, we have the association of the core collapse supernova with the high energy counterpart. And it was an event that was really, really nearby. Instead here, we have the spectroscopic confirmation of this association for an event redshift between 0.1 and 0.2, so of cosmological origin. And also we could really see at the beginning the afterglow emission, and then the evolution towards the kilonova broadline type 1c supernova, sorry, emission. Okay, so this was really one of the major conclusive proof of this association. That then, okay, we had many of such events in the years. So then we have some, as I said, very few cases where we could start the observations at very early time, okay? And also we could do it with a new instrument installed on the VLT that is UVES, that has the characteristic of having a very high resolution, let's say 40,000 of average, okay? And with this very exceptional observation, we saw that there was really plentiful of information if we were able to observe at early time the afterglow and with a spectral resolution higher than the first one that was very poor, that could be a few hundreds. Instead, here we have 40,000, as I said, as a resolution. So you can see here, just in a very small wavelength coverage, okay, just a few Armstrong, a few hundreds of Armstrong, we have a lot of absorption lines. Here again, the same is just the next part of the spectrum with a lot of absorption lines. So in this sense, the real revolution came in 2004 with the advent of the SWIFT satellite and also with the new technological improvement that was made by ESO, that is rapid response mode. So SWIFT, why? Because SWIFT was very able to quite precisely localize already the gamma ray event, but with this very quick capability of slewing, it gave us the position in the X-rays and maybe in the optical with very high accuracy, okay? Some are seconds, very few are seconds, let's say. And furthermore, the very important point is that all those information were immediately available to the observers, okay? So this really was a game changer in our observation, in our follow-up of GRB afterglow with the VLT. And the rapid response mode is this possibility at VLT that if you have an approved program using rapid response mode, for if you have, for example, a gamma ray burst afterglow that is immediately visible from and observable from the VLT, you can interrupt immediately, instantaneously, all the observations that are going on and go and observe the afterglow, okay? So this really improved the possibility to be early on the spectrum and so to add more access to much more information to do science, okay? So as you can see, just to give you an idea, the combination with the SWIFT capability with the target of opportunity or rapid response mode at ESO gave us really the opportunity to be on target within, let's say, minutes in the rapid response mode case or few hours in the case of target of opportunity. So at that epoch, there were like mostly two groups doing GRB follow-up at ESO. Then also other people, but mostly most observations were carried out by these two groups. So one of it was the Mystici group that was mainly based of Italian researchers because they were part of SWIFT. Some, of course, some UK people and also some people of SWIFT. So like Neil Garris to say, so the PIs and main researchers of SWIFT. And then there was another group that put together all the countries, say European countries studying gamma ray burst, but not part of SWIFT. And like, for example, Danish people from the Netherlands and Spain and so on. Okay, so it was a really strong competition, tough competition between those two groups, because with the advent of SWIFT, everyone was looking to have the most important result, for example, on the spectra of very ratio gamma ray burst or some very peculiar light curve or something like that, okay? So ESO tried many policies to make these two groups work together. Why? Because both of them had proposals that were very highly ranked by the panels, but were competing on the same science case. So ESO didn't know how to deal with that. And because of course you can imagine if you give time to both groups, as soon as you have an alert, both groups triggers the observation. So it was not clear the data that were taken belong to whom, to the first one that triggered, but if the other one triggered just 1 second after, so it was a lot of political issues there. So we had some times where we ran like one group had the observation in January, the other had the one in February, and so on, March, April, May, and so on. Another policy that has been tried was to have all the observation immediately public to both groups or immediately public to everyone. So we work under very different policies that ESO tried to set up to have this collaboration working properly. So I show you here some example of the results that we could obtain. Here is a paper from a theorist, but using also observation coming from VLT. So there has been a lot of paper putting together X-ray data from Swift and optical data, try to find the jet breaks, and that then brought to the conclusion that very often in X-ray and in optical we have different behaviors, because in X-ray we can have the plateaus, the flares, and so on. And at the end, after many, many years of observation and a lot of data taken, this problem of the difference in behavior in the X-ray and optical is still not set. There are still many explanations possible for the plateaus and flares and so on. So again, here is to stress that we could follow a lot of gamma ray bursts down to very deep magnitude, okay? So the afterglow imaging was performed for very faint sources because we had a lot of time to do that. We don't have this time now, okay? Nowadays, this would not be possible. So then from the spectroscopy, there was kind of, let's say, many amazing results, I would say. One feature that is very important is the presence of what we call fine structures lines. So fine structures lines are very peculiar of gamma ray burst and of some kind of quizzes, but much more rare. And those lines are transitions, comes from transitions that are not, usually you shouldn't have them, okay? So they comes from level that usually are not populated because they go immediately into the ground state, let's say. For gamma ray burst, we have these transitions. Now, then I will tell you why. But also, this transition, we saw that if we could be on target early and take a time series of spectra, we saw that this transition varied in a very evident way. So here you have an example of a spectrum taken at 8 minutes here. This is a fundamental state line, no problem. And this is the fine structure line, okay? So at the very beginning, these lines can be huge, can be really strong. And after a few hours, here is very early, but it can be also after 5 or 6, 7 hours, let's say more, they disappear and the ground level signatures increase, become stronger, okay? So studying this line variation of the fine structures line, we can determine the distance of the cloud, of the interstellar medium clouds that we are probing from the gamma ray burst, okay? So, yes, sorry, here you're missing information. In fact, yeah, here was it. The population of this level is really peculiar to gamma ray burst because it's due to the UV pumping that is caused by the JB X-ray mainly and UV afterglow radiation, okay? So you have these levels that are populated mainly by this extreme phenomena, and then as the radiation fades, you have the levels that become empty as again, and therefore you have less and less absorption from these levels and you have more absorption for the fundamental states, okay? So we collected a lot, for us is a lot, those such numbers are a lot, cases where we could perform, we could detect fine structures line and perform some time spectral variation. And we could determine the distance of these interstellar medium clouds. And you see that we are pretty close. We are really probably in the star forming region where the GRB exploded. In any case, the gas within the GRBOS galaxy. And okay, not the very close by one because it's ionized by the radiation. Okay, so we don't have the transition in the optical, but we will have them with Athena, for example. So this is it can be considered as incredibly powerful because you can probe the ISM of the star forming region of galaxies up to the highest redshift using gamma ray burst. Okay, and this in principle for any kind of star forming galaxies. Okay, you cannot do such kind of studies with current galaxy studies, for example. So then the other major result we had was from the discovery of a very high redshift gamma ray burst at redshift 8.2. And here, as you can see, this is a great discovery, but the information from the data is really poor, apart from the redshift determination. And this is due to many reasons. So first is that we were limited by the, okay, we arrived pretty late, but for a redshift sources is not so such a problem. But we were limited by the force spectral coverage that is limited to the visible part of the spectrum. So didn't really cover this part of the spectrum we were interested for such a redshift sources. And also UVES, that is the other instrument that we can use, is also limited by the spectral coverage, but also in sensitivity. So faint targets are observed with UVES will not give you high enough signal to noise to do some science, okay? So here, two instruments were used to cover the separate part of the spectrum, okay, and be able to probe this very redshift nature. So it was clear that we had the problem from an instrumentation point of view, that we are not, let's say, the best ones, the most suitable ones for such kind of observation. And then a new revolution from our point of view came with the advent of X-shooter. That is a unique spectrograph. VLT is the only telescope having an instruments like that is able to cover the full range of wavelength from the ultraviolet to the near infrared in a single shot with a pretty good resolution and with good sensitivity. So here the game of the rules of the game changed again, because we were not anymore divided into Mystic and Grace, but we had different groups having access to VLT time. One big group that joined to which belonged some people from Mystic, some people from Engraved, that were that were formed by the Shooter Consortium laboratories, okay, and then other groups external to the Shooter Consortium, but also there were also separate proposals focused on short gamma ray burst. More than one proposal from different groups within the Shooter Consortium, and the same for the low redshift supernovae. So with the Shooter, we did a lot of work on the redshift determination of gamma ray burst. So these are the distribution of redshift of all the gamma ray bursts, and the Shooter really contributed to a lot of them, especially at high redshift. Consider that this comes from 1997, all the purple sample, and the Shooter started the operation in 2009, okay? So we also give a good contribution to the metallicity determination of the ISM of the GRBOS galaxies, and so the evolution of metallicity in the universe. Here you have the color points are from gamma ray burst afterglow, and you have from the literature in red and from X-shooter in blue. And this is a kind of an old compilation. So from more or less 2013, adapted 2015, but we have more cases. And then we had, for example, very importantly, we were able to directly detect molecules. So H2 molecules, for example, we have also carbon oxygen molecules. So those are really direct detection of H2, not like in the millimetric observation where you have CO that you transform in H2. This is H2 at high redshift. In this case, redshift almost 3. Okay, so you can determine the column densities of H2 and compare it with the one on NH1 along the GRB line of sight and so on. And this was really possible thanks to X-shooter, because those systems are usually dust rich or metal rich, and therefore the afterglow is a bit fainter. So and you need on the other end some resolution to detect them. And with the UVs, they were often too faint to be detected, the afterglow were too faint to be able to perform spectroscopy. And instead with X-shooter, we can combine the resolution and the sensitivity to perform such studies. And then I wanted also to show you the fact that we can observe within the same spectrum, thanks to the wavelength coverage, we can observe the absorption lines and the emission lines from those galaxies. So we can have access to both information. This is also very, very difficult to be done in galaxy studies, especially at high redshift. You will have the emission, you will not have the absorption. So this is something for which gamma ray burst afterglow spectroscopy can be very useful. And then we perform some statistical studies, since we have this huge sample of gamma ray burst afterglow observed spectroscopically. I wanted to show you here the compilation of the neutral hydrogen column densities in function of redshift of the gamma ray burst host galaxy that we studied with the shooter. And here, this compilation was done in order to see if we had statistically, how many systems do we have that could contribute to reionization, okay? So to have a system for which a Lyman limit photon can escape, you should have very low neutral hydrogen column densities. And as you can see, those are pretty rare. So we use this sample to put strong constraints on the possibility, the reionization coming from star-forming galaxies in the universe. I invite you to read this paper if you're interested in. And also dust studies. So this is again a spectra of a GLB afterglow observed with X-shooter after almost 9 hours and then 30 hours. And as you can see, you have this huge absorption here that is still unexplained. So there is a paper about it, but with not solid explanation. If you think it can be done by, for example, the bump, the 2175 Armstrong bump due to the dust absorption, this is not the case, because it's very small. You should expect something very small. Instead, you have a huge thing. So, and it varies with time. So this is still unexplained, but it gives you an idea of the kind of dust studies that you can perform with gamma ray burst. Then again, another amazing result of the VLT observation of gamma ray burst is the detection of the kilonova associated with the gravitational wave event 170817. This is really an amazing set of spectra, okay? Here I have no doubt in saying that they are the best in the world for such event, because they could monitor both the blue part and the red part of the kilonova, and also its variation with time and the presence of these bumps that is supposed to be due to lanthanide's production in the kilonova. So now the situation now is that we are all together. Why? Because we started seeing that all these proposals that the different group had, like there could have been like more than 5 proposals dealing with gamma ray burst, even 7, 8, I don't know, something on this order. They had less and less success, in the sense that the remarks were, what do you do more than the other one? Is this just incremental, or so on? So it was clear that ESO was pushing all the group in Europe working on gamma ray burst to join together and go with the single proposal. And this is what we did. So we are now all together with a large proposal, a wide proposal that covers photometry, spectroscopy, polarimetry. I didn't talk about it because I'm not an expert of it, but there are also some very nice studies with force polarimetry of GLB afterglows. And we study both long and short gamma ray burst. So we have this huge proposal where we are all together. There is still a separate proposal that is focused on low redshift supernovae, okay? So associated with gamma ray burst. So this is a separate one. And all this proposal where we are all together is called the Stargate collaboration. So this group that we built, and we have now a large program at ESO, so a program that lasts for more than one semester, and is led by 3 PIs, as you can see here. So, okay, some result. I will go quickly here because I'm already almost out of time. So some recent result we had with within the Stargate collaboration is, for example, the detection of Lyman continuum leakage from a GLB afterglow line of sight. Here you have the IgM forest, and here you have the photons that are leaking here at the Lyman limit. Okay, and here you can see that we have a trace that is above 0 on the blue side of the Lyman limit. Okay. So we are also performing, of course, all the study that I mentioned before, that they go on, they didn't stop, but this I'm only showing some new results, let's say. And then we were also able to obtain the spectra of the GLB afterglow that has been observed at very high energy by the S and MAGIC Cherenkov telescope arrays, and in these spectra are really, really rich of information. So we are working on them, is a lot of work, but stay tuned for a new result about that. So I wanted to stress some improvements that we have now that within the Stargate collaboration. So we can perform RRM, so rapid response mode, with the possibility of changing the instrument, because since now we could perform rapid response mode observation only with the instrument that was already mounted in the telescope. So a lot of our triggers of the rapid response mode failed due to the fact that the instrument that was mounted wasn't the one we needed. Okay, so I already said that we are running a large program. And also, since we include also the photometry, in principle, we are independent from an afterglow detection point of view. That means that we don't have to wait to have the information on the afterglow, optical afterglow localization from another telescope to trigger our spectroscopic observation, okay? This is true to a certain point, because to do that, we have to use, for example, for faint sources, we have to use force photometry or OCI, that is the near infrared instrument photometry, and that takes time. So there is a time to observe the source, the time to have the data, look, find the position of the target, and then activate the spectroscopy. It's not a lot of time, but many times is enough to make the object not visible anymore from the VLT. So we miss the target, in fact, okay? So most of the time we rely on external telescope, let's say, and but in that case, we are limited by the lack of information in the near infrared, okay? If the afterglow is faint, or if it is in the near infrared, it is very difficult to have an external facility that will give you the information on the magnitude immediately, so that you can start the observation with the VLT before the object is not visible anymore. Sometimes you have a window of just a few hours. Furthermore, on X-Shooter, we have an acquisition camera that can perform photometry, but not in the near infrared, surprisingly, since X-Shooter is also covered the near infrared part from the spectroscopic point of view, but we miss a good near infrared acquisition facility. So this is why, this is how and where I think the COLIBRI and SVOM can play really an important role. SVOM, because it will increase the number of bursts that will be immediately visible from the VLT, and the COLIBRI, especially if it is equipped with the near infrared filters, because it will be able to detect the near infrared counterparts and disseminate quickly the information. About very high redshift gamma ray burst, though, I'm not very positive, because we are limited by the satellite's performance, in the sense that as can we see from this population study made by Giancarlo Ghirlanda a few years ago, that if you, in this plot, you have the e-peak, the observed e-peak of the burst and the flux. So, and you have the gamma ray burst observed by different satellites. So, and in yellow, you have the distribution of the very redshift population of gamma ray burst. So, as you can see, current satellite, but Swan will not change so much these numbers, are not really sensitive to the parameter space where the gamma ray burst redshift more than 5, covered by the gamma ray burst redshift more than 5, okay? So for this, to increase the number of very redshift gamma ray bursts, we have to wait for a new generation of satellites like the Theseus one. So I have the last 2 slides that are about present and future synergies with the Stargate and the TESO more in general. So one synergy that we already have is with the Engray collaboration that is focused to the follow-up of electromagnetic counterparts of gravitational wave sources, okay? So, for example, is that the kilonovae are observed by the Engray collaboration or by the Stargate, or if there is a short gamma ray burst, if it is a short gamma ray burst associated with the gravitational wave event, the electromagnetic counterpart observation will be performed by Engray. If not, they are under the Stargate umbrella. So there are disagreements between the collaboration also because the core of the people of Stargate, of the Stargate collaboration, has also some key roles in the Engray collaboration. So we communicate very well and we collaborate very well. A major future synergy that will not be so easy at ESO will be with the SOX instrument that will be installed not at VLT but at NTT and will be operational from half 2022. So the SOX instrument has been made by ESO with the goal of performing transient observation, in particular transient spectroscopy. Okay, so it is a medium resolution instrument with a pretty large wavelength coverage. Okay, and is really done to systematically follow up the event that comes from triggers or alert, like supernovae or collapsed supernovae and gamma ray bursts, for example. Okay, so for example, one can imagine that in the future, this will be the instrument that will measure the redshift of gamma ray burst. Okay, instead, for the most interesting case, or when we have bright cases that can be observed more than once, or very redshift cases, or cases where we think that the VLT observation are really useful, those will be followed by Stargate. Okay, but for example, if there is a burst like a bit faint that is visible from VLT only after let's say 10 hours after the explosions, is very likely that is SOX that will take the spectrum. We will not use VLT time. Though these are just predictions that I gave you because the discussion among the 2 groups are still to be done, and they will not be very easy, I expect. So this is a future synergy that will be very important. Also in the context of SVOMES will be very important. And that was my last slide. So thank you very much for your attention. Sorry if I have been a bit long.
Thank you very much, Susanna. I think that it was an excellent presentation. Then we can start with the questions. Stéphane, please.
Yes, very, very technical question. It was a very nice talk, Susanna. You trigger me some question concerning the rapid response mode of LISO. Of course, I'm thinking to SVOM. What are the overhead? Because we have spoken of the overhead, but what is the scale of this overhead? 5 minutes, 10 minutes, 1 hour?
10 minutes, 10 minutes.
It's 10 minutes. And how it works technically, this mode? You have a quota?
No. So the 10 minutes, if you have to change the instrument, if not immediately, you really don't have overhead. It's immediately like 1 minute, something like that.
Okay.
The
Imagine
if the instrument is already mounted, you just have to point the telescope, because the observation are interrupted really abruptly, in the sense they are not even registered. Okay, the observer will miss those data. So
Okay.
the telescope goes on the gamma ray burst target. Okay, so in case you have already the right instrument that is mounted, this is really 1 minute, let's say. Instead, if you have to change the instrument, is about 10 minutes. So the number of RRM triggering that we can perform depends on the one that we asked during the proposal. Okay. We really ask for few of them, let's say 1 or 2 per semester, because we saw that it happens very rarely that, unfortunately, that an afterglow is immediately visible from Paranal during nighttime and with the right visibility, let's say. So this is the situation.
Okay, it's only few. Okay.
Yeah, really 1, maximum 2 per semester. We don't ask more than that, and most of the time they go unused. It's really a very rare event. On the other hand, it is very important to keep it, because in the case where we have this event, when we trigger a REM observation, the observation have really amazing information compared to a normal spectrum of an afterglow. Also because it means that we can follow the burst and take more spectra at different time, usually when we have RRM triggers, because it means that the source is bright enough, let's say, and because we are early on target.
Okay.
And the activation is done automatically, Stéphane, if this also was the question. There is a software, a piece of software that doesn't need a human intervention.
Okay. So it would be nice to have more detail later, but it can be done in the framework of OSWAM.
Could you tell us something about your strategy of observations of kilonovas? Because, well, I know that the area of probability from the LIGO collaboration is huge. Then how do you decide what target to follow up?
Okay, so this is done under the ENGRAVE collaboration, and the ENGRAVE proposal is for the characterization of candidate counterparts. Okay, so we do not perform at VLT the search for the counterparts normally, let's say, but we go and observe the candidate counterparts that are found by other surveys and by other telescopes, and that seems to be promising kilonovae or electromagnetic counterparts. So let's say in most cases it should go like that. There is the gravitational wave event. Small telescope with a wide field of view or transient survey scan the error region, find possible counterparts, and in case there are ones that are really good ones, really good possible counterparts, with the ENGRAVE, so with VLT, we take photometry spectroscopy of such counterparts. Okay, in the case when the error region is from the gravitational wave interferometer is very small, we may perform, and we did it, we may perform a galaxy targeted searches for the counterpart. So if the region is small, we go and look at the most probable hosting galaxies of the gravitational wave event and take imaging observation of those to look for the presence of a transient.
Okay, thank you very much. I don't see more questions. Maybe someone who cannot or who don't know how to raise the hand. If you want to ask something, you can open your mic. It's okay. Okay, if not, we thanks again to Susanna.
Thank
Thank
you
you very
very
much.
I'm sorry, but I have to leave because I'm also having to attend another workshop. So I'm really sorry, but I have to say bye.
Don't worry. Thank you very much, Susanna.
Ciao,
Thank-
Susanna.
Thank you. Bye.
And we can continue with the presentation of Dany, please.
Here I am. Okay, you see me? Yes.
Yep.
Okay. Here we are. Okay, so you see my presentation?
Yep, perfect.
Okay. Okay, well, first, thanks a lot for the invitation. It's a pleasure to talk about this. Actually, it's a work we did, it was published a year ago, and we worked, large part of the work was done by my postdoc, Mikhail Besnogov, who suffered for a long time to do this calculation and understand all the physics that was needed, and was in collaboration also with Enrico Ramirez Ruiz, actually the one who asked a question several years ago about what is the luminosity of a very, very young neutron star, which now we dubbed it as a neo-neutron stars. And with the idea that maybe something like this could be observed as a hypermassive neutron star that would survive after a merger in a short gamma ray burst. And here's the reference for the published paper. So the idea of my talk, I will briefly review what we consider the structure of a neutron star. Then I would mention what is a proton-neutron star in its evolution and compare it with the born-again neutron star, which would be the neutron star, the hot neutron star formed in a merger, or maybe an accretion-induced collapse of a white dwarf. Then I would show briefly the thermal evolution of a neutron star from very, very early time to millions of years old, and show that in previous model there was something seriously wrong. And so here I go to describe our work on neo-neutron star, describing the physics of the low density layer, which are what control the thermal luminosity when the star is very young, the first few days or weeks where we could have observation in a merger.
I don't know if you have changed slide, but we still see your title slide.
You still see the title? You don't see the slides changing?
No.
No.
Okay.
Me
Confirmed.
not.
So I guess I have to share the full screen instead of.
No, okay, it was, we have seen it just a second before. We have seen it.
Oh, so it takes time to.
Yeah, okay, now we.
Okay. No,
Yeah,
you see
we see it now perfectly.
You see it, okay. Okay, so I will describe the basic physics for the low density part, which control the early evolution. Then I would describe the evolution at the time when the luminosity is close to the interluminosity, and then I would compare and with possible observation and conclusion for future prospect. So the origin of a neutron star, here is my nice view of it from Google Earth. So this is the Valley of Mexico. We can see the volcanoes nearby, the Popocatépetl, Iztaccíhuatl, the Titlaltépetl, next to it, the Sierra Negra or Titlepet, and this gray spot is the Mexico City. No? So I mentioned the Titlepet because that's where we have the two large Mexican observatory, the large millimeter telescope and the HAWK, the Walter Cherenkov observatory for high energy photons. Actually, you can even see it on Google. And here's a nice view on Google Earth of HAWK, which clearly show this, hundreds of water tanks. But okay, I go back to my Valley of Mexico and I put here a neutron star. So this is a neutron star on scale. It has about 25 kilometers in diameter. So it is smaller than the city of Mexico. Mass of 1 to 2 solar mass. The central density about 10 to the 15 gram per cubic centimeter. So that means 1 billion tons per cubic centimeter. And for comparison, if I would take all the buildings that are in Mexico City and compress these to neutron star matter density, the full city fits in the bottom of a teaspoon. It doesn't even fill a teaspoon. And to look at internal structure, well, that's what I do with my colleague at UNAM. So we drag here the campus, the Olympic Stadium of the Pumas, and the Astronomy Institute is just behind this logo of the university. So let me pull the neutron star toward us. What we see at the surface, of course, we have an atmosphere which is about 10 centimeters thick because of the extreme gravity. 10 to 20 centimeters below the photosphere, the matter becomes liquid because of the compression. So we have an ocean that would be a few meters or tens of meters deep, depending on the age and the temperature of the star, of course. Now, if I cut a slice of it, I can see below a layer of about 1 kilometer, which will be relevant precisely for the early evolution of the star. This rapidly crystallizes and form an extremely robust and rigid crust, which is also a metal. It's a very high thermal and electrical conductivity. And in the center of the star, we have the core where the density is higher than nuclear matter density, which is basically a quantum liquid of neutrons and protons and probably forms a superfluid. So now, how does this star is formed and what its early evolution? Well, you remember that a low mass star will form a white dwarf, but stars which are in the main sequence about 8 solar mass can end up after a supernova is a neutron star black hole. We don't know exactly what the critical mass to determine the outcome as a neutron star black hole. It depends also very strongly if the progenitor is a single star or in the binary system. But once the star is formed, we have what is called a proto-neutron star. So you have the iron core of the progenitor, which was about 1.4 solar mass, collapsed, and the moment of big crunch that here in this profile, the temperature time t equals 0. So this figure are from the paper of Burroughs and Latimer, the birth of neutron star, when these two people have the good idea to publish 5 or 6 months before the supernova in 1987 a detailed model of the birth of a neutron star and the prediction about the evolution of neutrinos. I think they knew that neutrinos and a supernova would be detected a few months later. For some reason, they had some contact with somebody else. So they have this very nice paper. It's called a proto-neutron star because it contains a lot of protons, so it's not yet a neutron star. No? The iron core that collapsed is about 45% proton and 55% neutrons. So it takes some time to convert proton into neutrons. And when you convert a proton into neutron, you emit a neutrinos, but very early on, because of high density and high temperature, the neutrino cannot escape. So you can have the inverse reaction that neutron mass plus the neutrino can go into proton plus electrons. So basically, to transform the proton into electrons, into neutron, you have to get rid of the electrons by transforming them into a neutrino, and you have to let the neutrino escape. And it takes about 10 to 20 seconds for the neutrinos to escape. So for example, here you see the temperature profile evolving with time up to about 20 seconds. You see here's the lepton fraction, so electron plus muon plus neutrinos. So initially it's about 35% of the total, and about after 20 seconds, we're down to about 5% of protons and 5% of electrons. No? So it takes about 20 seconds to get rid of the leptons by letting the neutrino escape. No? Here also this is the neutrino fraction, and after 10-20 seconds, the neutrino fraction is 0. So they basically left. So after this phase, we have a neutron star, not anymore a proton neutron star. So in 1987, these neutrinos were observed. No? 8 was seen in IMB and 12 in Kamiokande. And okay, so that's the scheme. Now, how is the neutron star going to be formed a little bit later than that? For example, have we been interested in the outer part when we have nuclei? very early on, the temperature is so hot that everything is melted. No? It took a lot of time for the progenitor star to make heavy elements, and then iron, this collapse. The moment of the collapse, everything that the star had done is completely destroyed. And there was just a quantum soup of neutrons and protons. And it takes some time until the nuclei can form again. So here is the model of Latimer and Swesti, and the density ran from 10 to the 7 up to 10 to the 14 gram per cubic centimeter. So above here, you would have homogeneous matter in the core, and that's where you expect nuclei to form. So you see that at temperatures of 10 to the 10 Kelvin and a bit above, then you go from a pair plasma with a gas of neutrons and proton, and you form the heavy nuclei. And here's the model of the evolution of a proton-neutron star by this group of Japanese colleagues. And starting from 5 seconds up to 2 minutes. And this red part show you when you have inhomogeneous phase, which means the nuclei are formed. No? And again, it's temperature between 2 to 5 and 6 MeV. Below 2 MeV, basically the nuclei have formed, and you already have a crust of a neutron star, which is maybe liquid initially and will crystallize with time. Notice about density of 50 times 10 to the 14 gram per cubic centimeter, then the matter is homogeneous. So this is a core. It's like a giant atomic nuclei with a large fraction of neutrons and only a few protons. And young neutron star we know, and we can help us to study very well, hopefully hot and young neutron star. Oops, what was it? No, sorry, I forgot that. Yeah. So this is similar, but instead of being a proton neutron star born in a supernova, that's a calculation of Stephen Rosberg. This is what I call a born again neutron star as the result of a merger. No? And here we show the temperature versus density, and then the electron fraction versus density. So of course, in the merger, you start with 2 neutron stars, so you have very small electron fraction, means small proton fraction compared to what you have in a supernova. No? But the temperature you have are pretty similar. No? This was SPH, so it's one of these dots is about 20 particles. And you see the outer layers after a few seconds, and some time. You get temperature of about 2 to 4 MeV. So you can expect rapidly after this, if the neutron star that is being merged survive, like a hypermassive neutron star due to fast rotation, it may have time to again form a crust. So it would be similar in some sense to a proton-neutron star forming a supernova. Now, the youngest neutron star we know so far, what we have one in 1987A, that probably have shown its first indication of its existence as a little blob of warm dust next to the center of the explosion that was seen by ALMA a few years ago. So we called it NS 1987A, neutron star 1987 in SN 1987A. Unfortunately, we don't see it. We only see the hot dust. And the youngest one we can see actually is in CAS A. This one is not 34 years old like 87A. It's 340 years old. No? It's just a little dot. So now let me briefly describe the evolution of these stars from birth. And so I'll show you a model where, like a small movie, on the left we'll see what we call a cooling curve, which means the effective temperature versus time. So up to about 1 million years, and starting with a very young 10 to the minus 8 years, not a fraction of a second. So young hot neutron star. And on the right panel, you will see the temperature profile inside the star. So, and the different layer we will have outside the atmosphere with the photosphere, density of about 10 to the minus 1, 10 to the minus 2 gram per cubic centimeter, down to the center of the star, a few times 10 to the 14 gram per cubic centimeter. No? So this part is cooling a little bit more rapidly than the rest because of neutrinos at the core, which is homogeneous neutron matter with a few protons. And then the outer layer, that's where we have nuclei. So with the crust, and the lower density part of the crust we call the envelope. No? So this is density that allows to see in detail the evolution of the temperature profile. But in terms of mass, the core is about 98% of the mass. And all this is about 2%. in terms of radius, let's say the neutron star is 11 kilometers radius, the core is 10 kilometers and the rest is 1 kilometer. So these are very narrow layers, but it was going to be interesting to study a very young neutron star. This layer that was going to control the evolution of the early part. So initially we would have a relaxation from the initial condition as a star when the star is born, either in the core collapse supernova or in a merger. Then at some time, the temperature stayed almost constant for a few decades, and that's where NS 1987A is, about there, 34 years old. And then we have a relaxation of the crust, and then the star continues evolving, emitting neutrinos, and later on, when the slope of the cooling curve changed, that's when the cooling is driven mostly by photon from the surface. So the next slide, I will show the movie. You will see the temperature profile evolving with time. And there's a little white dot, yellow dot, which corresponds to the photosphere. We just go down the stars. No? So it starts very hot and cools down. So this will mimic about a few 100,000 years of evolution. So we have a pretty complicated temperature profile in the outer part. All this evolution is driven by neutrino. I will describe more detail later. Here a plateau when the surface temperature model doesn't change. And then basically most of the star has either uniform temperature and only in the outer layer, which is a tiny fraction of the mass, we have a strong temperature gradient. So basically that's the scenario. No? But there is something interesting here that at this time, which is about 10 to the, a few times 10 to the minus 6 years, this model predicts a luminosity of 10 to the 41 ergs. Very early on, we get 10 to the 43 ergs per second. So that's orders of magnitude about Eddington luminosity. So obviously there's something wrong in this. No? Actually, not surprising, this model were not designed to model correctly the very early phase of the evolution of neutrons. So there are no data there, so nobody cares. We just put the physics was used here, the physics that's correct for later time. And you turn out that the code doesn't crash, so you get this early temperature, but it could be completely wrong. And actually that's when the question of Enrico came. It's okay, when we see this curve, what's really going on here? Very likely, we could assume that the star is going to be stuck at Eddington luminosity early on. We see this, for example, in X-ray burst, when you have also an enormously high luminosity coming from inside the star. There are many bursts which are called photospheric radius expansion. So these X-ray bursts are reach Eddington luminosity, and what happened, but just the luminosity blow off the outer part of the star. So all the extra energy coming out is used to push away the matter. And the luminosity reaches Eddington and stays at Eddington. And what is seen is that the surface becomes cooler because the radius expands. No? Actually, sometimes the star even disappears from the X-ray detector because it becomes because of the lower temperature, it moves out of the detector windows. No? And when the luminosity decreases below Eddington, the photosphere contracts again, it becomes hotter, and the star reappears in case the satellite doesn't have high sensitivity at low energy. So we should reasonably assume that early on the star will start at Eddington luminosity. But then the question is, how long can it be at Eddington luminosity? No? X-ray burst, it lasts a few seconds. And but a neutron star born in a supernova or in a merger, since all this is wrong, we have really no idea. Is it going to last 10 seconds, 10 minutes, 10 hours, 10 weeks? And so we have to put the correct physics and see really what's happening. So that's what we did with Mikhail Vesnogov. So let me briefly describe the physics that we know we need in these low density layers. We need neutrino for most of the cooling, the thermal conductivity, and the specific heat. So here I show this contour. The color shows the contour for the neutrino emissivity in ergs per cubic centimeter per second. And so the temperature versus log of density. So this is the outer part, the N block, which is going to control the surface temperature and the photon luminosity of the star during the first few weeks. So at high temperatures, dominant process is pair annihilation, because here we have a plasma of electron-proton pairs mostly. So pairs can annihilate and emit a pairs of neutrino and antineutrino. Most of the time they would emit photon, but photon cannot escape, they stay there. So for energy balance, neutrino are important because the neutrino will escape. When the temperature decreases, the pairs disappear because we don't have enough energy to produce positrons. And the next mechanism is plasmon decay. So plasmon is like a photon in the medium, which is like a massive photon. So it can decay into a pair of neutrino, antineutrino. So this is in density range. This white dot marks the shift from the pair and emission to plasmon decay. And you see the difference in the shape of the contour line. And when the temperature drops further, it goes below the plasma temperature of the medium, so there are not plasmons anymore. So this process shut off rapidly. And what is left is electron-ion Bremsstrahlung illustrated here. So it's like a normal Bremsstrahlung process, but instead of emitting a photon, the electron will emit a W0, which decays into a neutrino and antineutrino. So this is a good source of neutrino, but it's much, much less efficient than the other one. So here we have very strong neutron emission that disappear. Look at the scale. We go from 10 to the 28 to 10 to the 2 gram per cubic centimeter. So we have 26 orders of magnitude in neutron emission. So here is going to be tremendously efficient, and here is going to be tremendously inefficient. Specific heat is also interesting. Here schematically, we have electrons, the nuclei, okay, and the photons and pairs. So pairs and photons have an energy which goes like T to the 4, so the specific heat goes like T to the cube. Electrons are highly degenerate, so for a Fermi gas, they generate electrons. The specific heat is just proportional to the temperature, so it's just a straight line. For the nuclei at very high temperatures, they are liquid, an ideal gas even. So the energy is 3½ kBT, so the specific heat is 3½ kB. Then they become an imperfect gas. It finally becomes a liquid here at some melting temperature. Then it crystallizes and becomes a classical crystal. And the specific heat is 3 kB per nucleus. And then it goes into the quantum regime below the plasma temperature. It goes to the regime of T to the cube. So just the temperature dependence of this curve shows that at very high temperature, the T cube will win. And the pair will give us a specific heat. Then when they disappear, electron will take over because it's proportional to T. Temperature drops, the electron contribution disappears again, and the nuclei will dominate. At very low temperature, the electron will dominate over the T cube again. So we see it here. In this regime, this is given, specific heat is given by photon and electron positron pair. Then it's given by the electrons. So this is this regime here. And then when the shape change, it's given by the ions or the nuclei. In the liquid phase, which is this part here, then when the nuclei form a classical solid crystal, and then finally a quantum solid, that's the bioregime here. So we will mostly scan this region in the early evolution of a neutron star. So we have to include the pairs and then the electrons and the nuclei specific heat. So the calculation I showed before that was completely wrong because we didn't have really the pairs in the early evolution. Also thermal conductivity and opacity. The thermal conductivity kappa K is related to the opacity by the typical formula. So at very high density and very high temperature, low density, the heat is transported by photon and the opacity is dominated. This is opacity, is dominated by the pairs. Then when pair disappears, it's electron scattering. So it's Compton and Thomson scattering, which dominate the blockade of heat transport. Oops. And finally, in this regime here, then heat transport is dominated by electrons. Photons become very inefficient, and this collision of electrons and the ions in the liquid phase. This marks the melting temperature. So you have a discontinuity in the conductivity when suddenly you form a crystal, and that is electron phonon scattering, and then a quantum crystal. So basically, that's the physics that go there. So let me describe briefly the temperature profile we get. So again, the temperature versus density. So a typical calculation. So this model assumes a steady state, so there's no time evolution. So you just solve heat transport from the surface of the star, that would be the photosphere, to the interior about 10 to the 10 gram per cubic centimeter. So this is something like a few tenths of meter of about 100 meters in thickness. Now the maximum luminosity we have here, that would be to the Eddington luminosity. And the line which we see here, so above here we have a gas of proton, neutrons, and a pair plasma. At this line, the nuclei form. So here we can talk about the melting of the ions and the crystallization. This is the melting curve. No? So in this regime here, nuclei form a liquid, and below they crystallize. And the electron-positron pairs appear massively above these lines. And this is the line where the matter pressure is equal to radiation pressure. So above here, the envelope is completely dominated by radiation pressure. So that's the difficult part, because this kind of medium is highly unstable. So it took a hard time to Mikhail to be able to handle this kind of calculation. So the key point on the calculation, we would treat this part as the outer boundary of our model, and this gray part will be actually treated dynamically by the cooling code. So we would follow the evolution here, the contraction of the layer, and the emission of neutrinos. So an interesting thing to consider that the one that has Eddington luminosity at the temperature of about 2 or 3 times 10 to the 7 Kelvin, so 20 million Kelvin. Look at the density of 10 to the 5, basically, the temperature will be 10 to the 9 Kelvin. So we do not expect to have higher temperature here in this regime, because immediately the outer part will expand, like in a photospheric release expansion X-ray burst. So we would have to start our calculation assuming the luminosity has to be there. The temperature has to be there initially. So here's our setup to follow the time evolution. So the initial condition, we start here at low density 10 to the 5. The temperature has to be order 10 to the 9 because it would give us Eddington at the surface. Deep into the envelope 10 to the 11, we use the result either from proto-neutron star or born-again neutron star that tell us it is about 2 or 3 times 10 to the 10 Kelvin, so 2 to 4 MeV. I had showed you this model initially. Where are they? That one, okay. So this is the temperature about 20 seconds in the outer layer. This is 2 MeV, no? So the outer part is about 2 MeV when it becomes transparent to neutrinos. And also in that case, for the merger, the low density part below 10 to the 10, 10 to 11, at the temperature of about 2 to 4 MeV, no? And therefore the nuclei will form. So that will be our starting point. I will focus on this region, and I will assume an initial temperature here 2 to 4 MeV and follow what's happening below. Now, I ask people who have done this kind of calculation. Nobody has done the low density part seriously, so we don't really know what's happening there. So we have to make some guess at what is the temperature at the end of this very violent phase. And it's the first time we were calculating this. But so our condition will be 2 to 4 MeV here, and at low density in this regime, 10 to the 9 Kelvin, which gives us Eddington luminosity. So if I go rapidly, so this back. Okay, so that we start from this point and we move it. So we try to move a little bit the temperature profile, and that we go from these two conditions, and that will give us simply different evolution early on, and we see what happens. So the question will be, how long can we keep Eddington luminosity? And here's the answer. So again, so this is early cooling curve, the same as I was showing in the animation, except in the animation, the curve was going up and it was reaching about 10 to the 41 and 10 to the 40, even outside the screen early on. Because this early part was completely wrong. Now, when we fix up the physics correctly, so we see that the luminosity stays initially in the phase 1, which is a relaxation from this arbitrary temperature profile. It stays about there for about 10 to the 3, 10 to the 4 seconds. No? So it is a few hours when we can sustain the Eddington luminosity. That's interesting. In X-ray bursts, this kind of phase lasts a few seconds. No? So for the initial question, can you maintain Eddington for a few seconds, a few minutes, a few hours, a few weeks, a few days? And the answer is a few hours at most. No? We get different evolution early on depending on the temporary profiles. We varying what in the most reasonable range, I mean the possible range from the boundary condition, from the proton-neutron star or the Born-again neutron star, and from the Eddington condition, we get different profile. This was interesting. We tried to get a too low luminosity initially, and it turns out that a little bit later, its luminosity increased because there is heat below that has to get out. No? So you end up in this range of temperature. No? So that's the initial relaxation phase. Then it becomes dominated by neutrino. And all these different profiles finally converge with a basically uniform temperature profile because all the heat is lost into neutrinos and it rapidly forgets what it had. So this is driven by pair annihilation neutrinos. Then it's driven by plasmon neutrino. Plasmon shut off, the cooling becomes very slow, and this part is given by the electron ion beam strahlung. No? So this was what I was showing here. No? Here, high temperature is pair annihilation, then plasmon decay, and finally electron ion beam strahlung. So that gives us these four different phases here. In this curve, we just turn off the pair annihilation neutrinos. No? And so we see the star just doesn't cool until the plasmon turn on. No? So this is definitely due to the pair annihilation in the outer layer of the star. No? And this is the same, but showing the temperature at the surface. Okay, so that's what I was saying. No? When we turn off the pair annihilation, so it proves that the early evolution of the star is driven by this pair plasma in the outer layers, which is something that was missing in all previous calculations. It's also interesting to see the cooling time scale. So the neutrino cooling time scale is just the neutrino emissivity divided by the specific heat, and that tells you how long it would take to cool down at a typical temperature of 10 to the 9, to decrease the temperature by 10 to the 9 Kelvin. No? So the time scale in seconds, at very high temperature, it takes about 1 second to cool down the layer, no? Minus 1 second, see. That's a very high temperature dependence of the neutrinos. Later on, it becomes very inefficient. No? And that's why the star, once you're in this regime, it takes many years for the temperature to evolve. No? And here an example of temperature profile. So we start at 10 to the 9 at the surface, which gives us Eddington, few times 10 to the 10 at the inner boundary of the envelope, given by the proton-neutron star of the Born-again neutron star. And this is the evolution temperature profile. In 600 seconds, this part already relaxed very rapidly by neutron emission. And slowly it goes down. And after about 10,000 seconds, then the surface starts to cool down and it also compressed. This shows you the isobars, constant pressure. So this region was at 10 to the 5 gram per cubic centimeter, gram per cubic centimeter, yeah, will slowly compress, but it follows a constant pressure curve, no, in this temperature gradient. Also, if we change the mass of the star, like for 1.4 or 2 solar mass, this is model A and C, and that is 2. There is very little difference. A little bit initially because the Eddington luminosity changed barely, and the different phase, but basically you have like a nice power law that goes from 10 to the 4 almost to 10 to the 8 seconds. No? We made a try to see, we have a 1D code, so it's spherical symmetry. We don't have rotation, but it's okay, what happened is the star rotates very fast, which you expect in a merger. So we just take a very low mass neutron star, which means very low surface gravity. So the star can expand much more. And that's the kind of behavior we see. So very low mass, low effective gravity. So the Eddington luminosity is lower. So it's not as bright initially, but then it follows basically the same evolution. So from this first calculation, it doesn't look like the fast rotation is going to change the results for the medium-term evolution. It only would change what's happening very early on. Okay, so what are the chances to observe this? In a supernova, it's impossible. We see in 1987, it took 30 years until we get the first sign of the possible presence of the neutron star. And it's not an observation of the neutron star, it's just a blob of warm dust in the center of the supernova remnant. So, and it may take a few tens of years until the matter expand and get dilute enough so that the X-ray from the surface can be seen. So this is a hopeless scenario to study the very early evolution of neutron star. That's why nobody done it before. But if the star is a newborn, born again, hot neutron star in a merger, or maybe an accretion-induced collapse from a white dwarf, that could be a possibility. And then we would have a chance to see a neutron star which is not surrounded by 20 solar mass of garbage, and we may have a chance to see it. So this X-ray luminosity from our neo-neutron stars, and compare with what we get in short gamma ray burst. So this is from the jet, and it's orders of magnitude about what we get from the surface of the neutron star. So this will never be observed. But short gamma ray burst means the jet is pointing toward us. That's what we see the gamma ray burst. So in that case, there's no way we can detect the neutron star. But if this with this off axis, and that interest for the 1708-17 event, and in that case, then the luminosity will not be initially dominated by the jets. So we can plot again here our neo-neutron star over time, and the first X-ray observation from Chandra. And it's interesting, the first one that was done about 2.5 days, that was the 24 kilosecond observation, they had an upper limit of 50 times 10 to the 38. This is Eddington luminosity of a neutron star. So my prediction here early on that we had a few hours when the star would be at this luminosity. So in the future, in case of a similar event nearby and the chance that a good X-ray satellite we would be observing there, we may have a possibility to see the newborn neutron stars in a short gamma ray burst, and in a merger in which we are lucky enough that the jet doesn't point toward us. Here for the comparison is the model from Margutti et al. Of the modeling of the X-ray data for 1708-17. So very early on, the neo-neutron star would dominate the X-ray emission. So we would have in that case a chance to observe it. So briefly, we could say this as a conclusion. So a neo-neutron star can sustain Eddington-like luminosity for about an hour. And very early on, the detail depends on the initial condition, but within a factor of 2. So it's not terribly bad. And the early luminosity in photon is comparable to the upper limit from Chandra. But the early, that means the first few hours, unfortunately, Chandra was 2.5 days. But in the future, we may have a chance to do it. Maybe better X-ray observatory and lock to have another merger very nearby. The evolution over a bit longer time, for days and weeks and up to 1 year, is basically a universal function. It doesn't depend really on the mass of the star and the details. So you have kind of a power law evolution. And maybe the most promising thing would be to see the collapse of a white dwarf into a neutron star, because in that case, you would not have the matter ejected by the remnant, and you don't have a jet. So that would be a much cleaner event. And there's possibility as a Palomar transient factory would be able to detect event like this, I think up to about 100 megaparsec. So that would give us maybe the best chance to see a bare neo-neutron star. What needs to be done, obviously, for the case of a merger, which very likely rotating very rapidly, may have very strong dynamo or twist of enrolling, producing very strong magnetic field by differential rotation. So strong magnetic field effect has to be considered, and they may change some of the results. And also a real model of in 2D with sparse rotation would be good. So we're working on that at the time. That's it.
Thank you very much, Dany. I don't see any questions. Please, Stéphane.
Thanks again. It was very nice, very clear, very pedagogic. I have just a very simple question on your slide 47. Have you tried to put the sensitivity of Athena?
No.
Because I suspect that it could work.
Yeah. No, we haven't done any detailed study of what really would be done for with the coming observatories.
So I think it could be a good exercise. Well, Athena is not tomorrow, but it will fly in the future.
Hopefully still be alive, yes.
Okay.
Okay.
Enrique, please.
Hi, Dany. Nice talk. So if I understood correctly, at the beginning, you mentioned that you could have a period where you had a luminosity, a super Eddington luminosity of, I forget, 10 to the 43 ergs per second or something like that. Is that
Yes.
from material that falls back after the supernova?
No, that was just from a wrong calculation.
Oh, okay. So it's not. Okay.
No, that was completely unrealistic. Because there's no data, nobody cared about this. So we just run the code and it gave that results. But the physics put into the code was completely wrong. But it was interesting precisely to say, can we have this, and we can have this very high luminosity for a long time? And it's totally unrealistic. If you have more than Eddington, immediately it's going to expand. We see it in X-ray burst. All this extra energy going to blowing away the outer layer. No?
So the only question there would be then that whether all of that is going into photons and not also neutrinos, right? If you were to have something like that.
Yeah, well, the outer layer is dominated by photons. It's never hot enough. And even here's the surface temperature is a few times 10 to the 8 Kelvin, so neutrino are negligible. You have to go well above 10 to the 9 in this regime for neutrinos to be important. So it's mostly photon. But the neutrino is what is cooling the star a bit below, no? And the surface is following what's happening below.
Right. Okay. Thank you.
Dany, I have maybe it's a very silly question, but what do you expect to see in the case of an interaction of a neutron star with a white dwarf?
No, you mean interaction? You mean the new neutron star born from a collapse of white dwarf?
No, in the conclusion, in your slide of conclusion, you said something.
Yeah, I mentioned.
Yes, the most promising future.
Collapse of a white dwarf. No, this idea is in a system where the white dwarf is accreting from a companion. So it's a scenario for type 1a supernova, that the white dwarf will explode. But if the conditions are right, instead of exploding, it would just collapse into a neutron star. So in this case, it would be kind of clean systems, not like in a supernova, core collapse supernova, when you expel a lot of matter and you cannot see the neutron star. In this case, it would be much cleaner, and you would really see just a bare neutron star with only a little bit of matter ejected. No? The neutrino from the hot neutron star are going to blow away some matter. No? But after for a few seconds. Then after this, you get the bare neutron star. So that would be the nice part.
Okay, I got it.
So it's accretion in a binary system, like a cataclysmic variable. No? But suddenly is the white dwarf collapse to the neutron star.
Thank you. Jean-Luc, please.
Yes, thank you. Thank you for this nice talk. I have a question about, you mentioned at the end the effect of very strong magnetic field.
Yeah.
What could be the effect? What can we imagine from the effect of very strong magnetic field?
Yeah, I think there is effect on heat transport, because when in the part where electrons transport the heat to the surface, the electron will move along the magnetic field line, but not perpendicular. But in the early phase, the heat transport is not very important, is mostly neutrinos. That's what is cooling the outer layer. And the pair annihilation can be affected by magnetic field, the electron-positron, no? That decay. And but nobody has calculated it. You would need definitely much more than 10 to the 14 Gauss to have some effect. But it hasn't been calculated, so it's a guess what it is. No? The other effect is synchrotron emission. No? Instead of emitting photon, you can emit a pair of neutrinos, anti-neutrino from synchrotron radiation, but that's not terribly efficient. So it would be pair annihilation. Somebody has to calculate that.
Okay, so thank you very much.
Well, I don't see more questions. Okay, nobody. Then we have Alan here, and I don't know if we want to say something. Jean-Luc, Alan.
Hi, Rosa. You wrote me, I just finished my class. Sorry, I couldn't be here for the talks. Rosa wrote to me and said I have to say something on instruments. So I don't have much to say, but let me say what I do have to say. Where is it? So this is Dragito at the moment. Okay, it's all packed in boxes in the institute. These are the computers and a lot of the auxiliary gears for the control system. This is the main structure of Dragito in this box here. This is fragile. This one that says Spectral Instruments, that's the service cabinet for the CCD. And then this wooden box here, that's the CCD. So that's stuck in our institute. We had the perfect storm of the start of the financial year when nothing happens in the UNAM and a red level, the highest level contingency because of COVID. So we couldn't go in to the institute to fix it. The contingency lifted a couple of weeks ago and we went in and finished packing. And on Friday, we received notification that the UNAM Shipping Authority will now accept the boxes to be shipped to France to be installed on the telescope. So we have a company coming in to put these boxes on pallets and to take them to the shipping agency. And from there, they will travel to France. And I would expect them to be there for the end of the month. So that's all I have to say about instruments.
Okay, thank you very much. Jean-Luc, do you want to add something?
Not really. We are very far from having boxes with our instrument inside. But we will have an important review within 1 month from now. After the review, we'll be able to start building the instrument. So the review will last from mid-April to beginning of May, something like that. And then at the end of the review, we will be able to start building Gageur.
Perfect. And what about the next quarterly meeting? Is everybody okay if it's in June?
Yeah, you can share your screen, Rosa. I know that you have prepared a slide.
Yes, I always have slides for everything. Let me show this here. Well, we have maybe, it's almost confirmed, the participation from David and Fabio De Colle. I think that everybody here know them. And then for June, this is what we have to prepare.
Yeah. just to be clear, David wants to present Messier or give some news of Messier. It's a low surface brightness satellite. A proposal.
Yes.
Huh?
Yes.
And Fabio, I don't know what he wants to present. Maybe you know.
I think so. He's my boss.
Oh, okay.
He works with numerical simulations, doing GRBs, jets of GRBs in general of the idea.
Okay. Okay.
Well, if we don't have more.
And I propose just to Alan is now connected that in June at this meeting we take an official decision concerning the physical meeting. Well, there is no guarantee but we have to take a decision for June. This is the latest limit probably.
Okay, I understand that. Yeah.
I'm not optimistic, but okay.
Yeah.
We have to take a decision in June because there is some impact on the budget.
Okay. If nobody wants to say something else, we can finish the meeting here. Thank you very much for coming. Thank you very much, especially to Dany and Susanna. And see you in June.
Yes, thank you very much. Take care of you. Huh?
Bye.
Bye.
Okay. Bye.
Thank you very much.
Thanks
Bye-bye.
to everyone. Bye.
Bye.
See you soon, hopefully. Bye.